This is a short video to review valence electrons and to introduce the Lewis structure or Lewis dot diagram way of showing valence electrons before you have a chance to practice drawing Lewis structures in class. So just a brief review. Remember that electrons live in orbitals rather than orbits, and these orbitals are at different energy levels. The periodic table shows us the 7 primary energy levels, and this corresponds to the 7 rows that we have in the periodic table. But in each energy level, we have various sublevels, sometimes also called subshells, because the primary energy levels themselves get known as electron shells. Inside each sublevel, we have different types of orbitals. We have S, P, D, and F sublevels with different numbers of orbitals in each. So there is one orbital that can hold 2 electrons in the S sublevel, no matter which energy level you are in. The P sublevel has 3 orbitals, so there's a total of 6 electrons. D sublevel has 5 orbitals, can hold 10 electrons, and the F sublevel, no matter what energy level it's at, though F is only found at the higher energy levels, will be able to hold 7 orbitals or 14 electrons. So if we have a little Bohr diagram of the model of the atom over here of neon, you can see our 2 primary energy levels, the first one in red and the second energy level in blue. In our first energy level, we have 2 electrons. Those are 1s electrons. And then in our second energy level, we have 8 electrons. It's a combination of 2s and 2p electrons. We use electron configuration as a way to identify the electron arrangement in any particular atom or element. There's 2 ways of doing that, the long way and the short way. The standard format is the long way, where we would write out every single electron starting at the very first energy level. So for carbon here, we have electron configuration of 1s2, 2s2, 2p2. And for sodium, we have 1s2, 2p2, 2p6, 3s1. Now I know that you've experienced in class how with some of your larger atoms these electron configuration formatting gets very, very long, and so the noble gas abbreviation is the way to go. And in this case you use the noble gas from the row above and then just add in the electrons that exist for that particular element past all the ones that are found in that particular noble gas. So for chlorine it looks just like neon, but it also has 3s2 and 3p5 electrons. For calcium it looks just like argon, but we add a 4s2 electrons. Now the valence electrons are the electrons found in the highest energy level. So in your electron configurations, you can find your valence electrons by looking at the electrons listed in that highest energy level. So in carbon, we have these 2p electrons. Those are our valence electrons. Or in sodium, we have the 3s electron as its valence electrons. Chlorine, we've got some in primary level 3. Calcium, our valence electrons over here are in the 4s2 electrons. So you can use the electron configurations to get a number of valence electrons. Valence electrons are important because they determine how an element reacts. And of course, chemistry is all about chemical reactions, and we're all curious as to how you can put 2 chemicals together and get a reaction. But when you get down to the nitty-gritty details, it's really all about electrons, and especially these valence electrons. The periodic table offers clues to valence electrons, especially when we're concerning the S and P sublevels. And if you remember, we have the first 2 columns in your periodic table are your S electron block, and then these last 6 columns are the P electron block. And so you can see some numbers on this illustration. This is telling you the valence electrons that are found in the elements that occupy those squares. And so we've got our 1s electrons falling in this first column or the first group, and then we have 2s electrons in the second group. Remember, the helium actually belongs over here, even though as a non-metal we put it in with the noble gases because that's where it falls chemically, but it contains just s orbital electrons. And then if we kind of skip over the transition elements, we basically can number these columns. So in this third column, we're having elements that have 3 valence electrons through most of that column. Same thing with the 4th column. When we get down to the bottom here, this section has some transition elements, some multivalent elements that are going to have more than one option, and so I've just put in the ones where we've got the single charge showing up for our valence electrons. So the same thing, 5th column 5 valence electrons, 6th column 7 columns. Our last column over here are noble gases, aside from helium, all have 8 because they have a full p orbital and an s orbital for whatever energy level they're in. So what can we do with these valence electrons? Well, the Lewis structure is another way to show valence electrons. It's a visual representation. It's a drawing of the valence electrons. And we do that by putting the electrons as dots around the atomic symbol. So we start with the atomic symbol and we add some dots. And it becomes very useful in the topic we're going to cover next, which is how molecules are put together. By looking at Lewis structures or Lewis dot diagrams, it really helps us figure out what this molecule looks like, and then that can be used to determine other properties of those molecules. So starting with sodium here, you can see it has 1 valence electron, and so right around the sodium we've just put one single dot to represent that 1 valence electrons. Carbon has 4 valence electrons, and so it has 4 dots around it. Chlorine has 7 valence electrons, so we have 7 dots. And then neon has 8 valence electrons, and so we have 8 dots. Notice, especially with neon, you can kind of see that there's a square around this atomic element. So the electrons are being placed on the sides of the square. Also, just like when we did the orbital filling diagrams here in carbon, electrons do not want to be next to each other, and so it is helpful to place the electrons, go all the way around once before you start doubling up. Even though if you think about the electron configuration for carbon, it's going to have a 2s2 where you're going to have 2 electrons together in that orbital. But we're not going to show that in doing this diagram because it is more helpful in determining molecular structure if we just keep those electrons separate until we have to start doubling up because there are more than 4. So your rules for writing Lewis diagrams are really quite simple. You write down your atomic symbol, pull it right off the periodic table, use the periodic table or electron configuration to determine the number of valence electrons. Think of that symbol as being inside a box, and then place dots for each electron on the sides of the box, 1 per side as you go around. So let's practice some. So how about the Lewis structure for magnesium? Well, magnesium, the atomic number, or the atomic symbol is Mg, and it has 2 electrons because it is found in the 2nd column. So we have 2 valence electrons. It's on the 3rd energy level, so that would be 3s2 electrons. And so it really doesn't matter what side you want to start on. So, if you want to start on the top and draw a little electron on the top and then over here on the right, that's fine. You don't have to start on the right-hand side. Just place 2 electrons around that atomic symbol as an example of the Lewis structure for magnesium. How about aluminum? So aluminum, the atomic symbol is Al. If you look to see, it is found in the 3rd column if we discount those transition metals in the middle. So we jump right over to the P block. So we have 3 valence electrons. So again, we're just going to put 3 dots, one side at a time until we kind of run out of electrons. So there's aluminum. This one's not quite as big here on the right, but our aluminum showing our 3 valence electrons. And then our last example here, phosphorus. Phosphorus, the atomic symbol is just a P. It is found in the 5th column, and so it is going to have 5 valence electrons. And so I think even though we're going to have to go around more than once, I think it just is helpful to just kind of go, okay, 1, 2, 3, 4, and then 5. Start doubling up. So just travel around that atomic symbol, hitting all of the sides of the box before you start doubling up. And that's really all there is to drawing Lewis structures. After you get this down, we'll be putting them together and making chemical compounds by talking about how it works for ionic bonds or covalent bonds. But this is the basics that I wanted to cover before we move into those more advanced topics.